Hello and welcome. Today we are diving into one of the most fundamental and versatile component in modern electronics, the operational amplifier. In short, we called it OpAmp. As you can see from this overview, we will cover everything from its physical pinout and circuit symbol to its internal model and operating characteristics. By the end of this, you will have a solid understanding of what an OpAmp is and how it works. To download our electrical engineering app, you can visit this website link electrical-engineering.app. It is especially designed for electrical and electronics engineering students. So first of all, what exactly is an OpAmp? So first, it's an active electric. Here we can see it is active circuit element. This is a crucial point. Unlike passive component like resistors or capacitors that only dissipate or store energy, an active element needs an external power source to function. So this OpAmp also needs an external power source to function. This power allows it to add energy to a circuit, most notably by amplifying a signal. Then its primary purpose is to perform various mathematical operations on voltage signals. As the note says, it can sum signals, amplify signals, and integrate it or differentiate it. This is where it gets its name operational amplifier. The specific operation it performs is determined by the external components like resistors and capacitors you connect to it. Then next is linear device. It considered a linear device but with a very important caveat that we will see later. This means that within its operating range, the output is directly proportional to input. So that's why it is called as linear device. Then fundamentally, you can think of an OpAmp as a voltage controlled voltage source. So it is a voltage controlled voltage source. This means the output voltage is controlled by the voltage difference between its two input terminals. Then next is integrated circuit IC. So finally a bit of history. Operational amplifier or OpAmps are integrated circuit, meaning all their complex internal circuitry like transistors, resistors, etc. is fabricated on a single tiny chip of silicon. The first monolithic IC OpAmp appeared around 1963 and one of the most famous and widely used OpAmp of all time is the IC741. So here we can see IC741 OpAmp is the most famous and widely used OpAmp of all time is the IC741 OpAmp, which the pinout we are about to see is based on. So now here we will see its pin configuration. So let's look at how an OpAmp is physically packaged. This is a common 8-pin dual inline package. Now this is a common 8-pin dual inline package or DIP. We called it DIP. The small notch, here we can see this small notch at the top helps you orient the chip correctly. That means we can identify from where the number 1 is starting. So from here the pin number 1 is starting. So from this pin 1 and this pin 5. So this is called as balance or offset null. So here we can see it is called as balance or offset null. These pins are used to correct for tiny imperfections in the manufacturing process. So they are just used for offset purpose or balance purpose. In the manufacturing process, it may be tiny imperfection in the manufacturing process. Ideally, if both inputs are at the same voltage, the output should be 0. So the output should be at 0. In reality, there might be a small offset voltage. These pins allow you to connect a potentiometer to null or 0 out that offset. For most basic applications, these are often left unconnected. So generally, for a basic application, we can keep this unconnected. Then let's see pin number 2. So here this is a inverting input. It is denoted by this minus sign. So for pin number 2, this is one of the two main signals input. So this inverting input and this non-inverting input. So currently we are seeing this pin number 2. So this is one of the two main signals input. A signal applied here will be amplified and appear at the output with a 180-degree phase shift. It will be inverted. Now here we can see, if we give this signal, then we get the inverting output. Here we can see currently the positive phase, then negative phase, but in the output we are getting negative phase first and positive phase later. So that is what inverting input means. We get 180-degree phase shift, or we can say the input signal will be inverted. Now next is non-inverting input, that is pin number 3. So this is the other signal input. A signal applied here will be amplified and appears at the output in phase. So at this non-inverting input, which is denoted by this plus sign or pin number 3, so here we get same output but amplified. There it will be in phase. So here we can see this is positive phase, this is negative phase. So at the output also we are getting positive phase and negative phase, but here we are getting amplified signal at the output. So this is for pin number 3. Now next is pin number 4. So for pin number 4, it is a power. It is for power purpose. This is the negative power supply connection, often connected to a negative voltage like minus 15 volt or to ground. So this is for power purpose, because this OpAmp runs on power. Then next is pin number 6. So pin number 6 is for output. This is where the result of the OpAmp operation, the amplified signal, came out. So here we get the output signal. We have seen this pin number 1 and pin number 5. Then we have seen this pin number 2 and pin number 3. Then we have seen pin number 4 is used for power, and then pin number 6 is for output. Then next is pin number 7. So this pin number 7 is for positive power. That means here we have to connect positive terminal of the battery, and here we have to connect negative terminal of the battery. So this is the positive power supply connection, typically connected to a positive voltage like plus 15 volt. So we have to connect it to a plus 15 volt battery. Then next and last is pin number 8. So here there is no connection. In short, we called it NC. So this pin is not connected to anything internally and is just there for mathematical stability of 8-pin package. So it is just for here on left side we are getting 4 pins. So that's why on right side also we are getting 4 pins, and the structure of this OpAmp is like a rectangular shape. Now next we will see this circuit symbol. So in circuit diagram, we don't draw the whole package. We use this standard symbol, a triangle. So basically this is the symbol for OpAmp. So here we can see the two inputs are on the flat side. So here this is the flat side of this triangle, the inverting input, so which is pin number 2, marked with minus sign. So here we can see it is marked with minus sign, and the non-inverting input with a plus sign. So here the non-inverting input is represented by this plus sign. Then next is the output. The single output is at the pointed end. So here this is the triangle, this is the flat surface, and this is the pointed end. So at this end we get the output. Then next, these are the, here we can see this is pin number 7 and this is pin number 4. So the power supply connected between this V plus and this V minus are often omitted from simpler diagram for clarity, but you must always remember they are there. They are there and need to be connected for the OpAmp to work. So to turn on the OpAmp or to run the OpAmp, we need to connect it to the power supply. So the diagram also shows how the inputs affect the output. A sine wave going into the inverting input. Here we can see this is the inverting input, and we are getting the 180 degree phase shift. That means we are getting inverted output from this inverting input terminal. Then for this pin number 3, which is non-inverting input, we are getting here the input and output both are in phase. So a sine wave going into the non-inverting input plus here this plus sign and comes out amplified and the right way up. So we are getting the amplified signal which is in phase. Then next, powering the OpAmp. So this diagram shows how the OpAmp is powered using a dual or split power supply. So here we are supplying using a dual or split power supply. We have a positive voltage plus VCC and a negative voltage minus VCC relative to a common ground. So here it is connected to a common ground. So here the current, here we can see the currents are also shown like this I1 and I2 are the currents flowing into the input terminal, which is this I plus and this I minus are the currents drawn from the power supply. So these are the current from these power supplies. Then IO is the current leaving the output terminal. So this IO represents the output current. Now here we can see by using KCL. Now this KCL stands for Kirchhoff's current law. So by Kirchhoff's current law, the sum of currents entering the device must be equal to the sum of current leaving. That means summation of all the currents entering a node is equal to summation of all the currents leaving the node. So here this box shows the equation IO is equal to I1 plus I2 plus this I plus I minus. So let's understand this. So we are assuming this as a node. So here the entering currents are, this I1 is the entering current at this node, this I2 is also entering current, this I plus is also entering, and this I minus is also entering. So these are all entering current, and leaving current is only this IO. So this IO is the leaving current only. Then next is a key property of an ideal OpAmp is that it has infinite input impedance. So remember that it has infinite input impedance, meaning I1 and I2 are 0. This I1 and I2 are 0 for ideal OpAmp. In case of a real OpAmp, they are incredibly small, like in nanoamps or in picoamps. So this current is very small in case of real or practical OpAmp, in the range of nanoampere or in the range of picoampere. So for most calculations, we can assume they are 0. This simplifies the analysis of OpAmp circuits. Now next we will see the non-ideal equivalent circuit. So here we can see this is the equivalent circuit of the non-ideal OpAmp. So first of all, now let's look inside the symbol. This is a model of what a real non-ideal OpAmp behaves like. So it has input resistance Ri. So here we can see this is the input resistance. This is the resistance seen between the input terminals. In real OpAmp, it is very high but not infinite. So in case of real OpAmp, it is very high but not infinite. Then next is Vd. So this Vd is basically the differential input voltage. This is the crucial voltage that the OpAmp actually amplifies. It is the difference between the non-inverting voltage V2. So here it is the difference between V2 and the inverting voltage V1. So here remember that this is the inverting voltage and this is the non-inverting voltage. Then the equation is shown. Here we can see Vd is equal to, so Vd is equal to V2 minus V1, where this Vd represents differential input voltage. Then next is the dependent source AVD. So here we can see this is the AVD, which is the dependent source. Now at the heart of the model is the voltage controlled voltage source. So we know that it is basically a voltage controlled voltage source. Its output is the open loop voltage gain. So open loop voltage gain is represented by this A. Here we can see open loop voltage gain is A. Then multiplied by the differential input voltage Vd. So we multiply it with this Vd, which is the differential input voltage. Now remember that this A represents open loop voltage gain and this Vd represents differential input voltage. Then open loop means, now why it is called as open loop? This is the gain of the op-amp by itself without any feedback components. So we can make it closed loop or open loop. So this is A is called as open loop because this is the gain of op-amp by itself without any feedback. Then next is RO. So this RO represents output resistance. So this is a small internal resistance in series with the output. Here we can see it is in series with output. This is a small internal resistance in series with the output. It represents the fact that a real op-amp can't supply infinite current. So it can't we can't get the infinite current output. Then next is the final output voltage is VO is equal to A into Vd. Again this A represents open loop voltage gain and this Vd represents differential input voltage. Then it is equal to A into V2 minus V1. We know that this Vd is V2 minus V1. Here we have already seen that Vd is equal to V2 minus V1. Then, however, this is only true when the op-amp is in its linear operating region. The output voltage VO can never exceed the power supply voltage as shown by the inequality. Here we can see this is the inequality. Magnitude of VO is always less than VCC. Now next we will see parameters. So here these are the OpAmp parameters, typical versus ideal. Now this table is fantastic because it compares the values for a typical real world OpAmp to the theoretical ideal OpAmp. So this is practical range and this is the theoretical or we can say ideal range OpAmp we use for simplifying circuit analysis. So for theoretical purpose we use these ideal values and for practical purpose we use this typical range. Then open loop gain. First of all, this first parameter is open loop gain, which is represented by capital A. So it typically ranges from 10 raised to the power 5 to 10 raised to the power 8. It is massive. Ideally we want it to be infinite, but ideally it should be infinite or we considered it infinite for theoretical purpose. Now a huge gain is what makes up OpAmp so powerful in feedback circuits. So this is about OpAmp. This is about open loop gain A. Then next is input resistance. So input resistance is represented by Ri. So its typical range is from 10 raised to the power 5 to 10 raised to the power 13 ohm in practical, but in ideal or theoretical it is infinite ohm. So this is extremely high. Ideally it's infinite. This ensures the OpAmp doesn't draw any current from the signal source it's connected to. Then next parameter is output resistance. Now output resistance is represented by Ro. So its typical range or practical range is from 10 to 100 ohm. Now this is very low. Remember that the input impedance should be high and the output impedance should be low. So always remember that the input impedance should be high and the output impedance should be low. So again, output resistance, which is represented by RO, typically ranges from 10 to 100 ohm. This is very low. Ideally it should be 0. A 0 output resistance means it can deliver its full voltage to any load without any voltage drop. Then next parameter is supply voltage or VCC. So VCC, it should be in practical 5 volt to 24 volt. So typically 5 volt to 24 volt. This isn't an ideal parameter but a practical operating requirement that also defines the limit of the output signal. So these are the parameters of OpAmp. Now next we will see output voltage and saturation. So let's understand this graph. So this is the graph for OpAmp output voltage VO as a function of the differential input voltage VD. So basically this graph is the key to understanding OpAmp behavior. It plots the output voltage VO against the differential input voltage VD. So this is VD and this is output voltage VO. Now here we can see the linear region. So let's understand one by one. So the linear region, this is the linear region basically. Look at very steep slope in the middle. This is where the equation VO is equal to AVD holds true. Now here in this linear region, VO is equal to AVD. And always remember that VO is less than or equal to minus VCC and AVD is always less than or equal to plus VCC. Because the gain A is so enormous, this slope is nearly vertical. Then this means even a tiny VD, it may be in microvolt, can cause a large output voltage. This is the region where the OpAmp acts as an amplifier. So in this region, the OpAmp acts as an amplifier. The range is defined as minus VCC less than or equal to VO is equal to AVD less than or equal to VCC. Then next is positive saturation. So in case of positive saturation, VO is equal to VCC. So if the differential input VD, if this input VD becomes even slightly positive, the output VO shoots up until it hits physical limit, which is the positive supply voltage plus VCC. So this plus VCC is the positive limit. It cannot go any higher. So it cannot go any higher than this plus VCC. This is called as positive saturation. Then next is negative saturation. Now similar to positive saturation, if VD becomes slightly negative, remember that if VD becomes slightly negative, then the output VO get down until it hits its negative limit minus VCC. So this is the negative saturation. So this is called as negative saturation. Now again, an OpAmp used open loop without any feedback is not a good amplifier. It's a comparator. Any small difference in input voltage will slam the output to either plus VCC or minus VCC. So here this is plus VCC or minus VCC. To use it as a linear amplifier, we must use a negative feedback. So to use this as a amplifier, we must use negative feedback, which is a technique that forces VD to be almost exactly 0, keeping the OpAmp operating on the steep linear slope. So in this region only the OpAmp amplifies. Then next is, now we will see the conclusion for this. So there you have it. We have gone from the physical chip to the circuit symbol and from the ideal model to the practical limitations of real OpAmp. The key concept is to remember are its high gain, high input resistance and low output resistance. Understanding these characteristics, especially the relationship between the linear region and saturation, is the foundation for analyzing and designing all kinds of powerful circuits, from simple amplifiers to active filters and oscillators. So don't forget to like, share and subscribe to this channel. And also, if you want to download notes, you can visit this website link, electrical-engineering.app. It is especially designed for electrical and electronics engineering students. There you will get these types of notes. So thanks for watching.